Download this code from codegive.com, link in the description below. Data structures in Go, hash tables, maps, a comprehensive guide. Hash tables, or hash maps, dictionaries, associative arrays, are fundamental data structures used for efficient storage and retrieval of data. They provide average O(1) time complexity for insertion, deletion, and lookup operations, making them incredibly powerful for various applications. In Go, hash tables are implemented using the built-in map type. This tutorial will delve deep into Go's map data structure, covering its underlying concepts, usage, performance characteristics, and best practices. 1. Understanding hash tables. At their core, hash tables store data in key-value pairs. The key serves as a unique identifier for the associated value. The magic of hash tables lies in the hashing function. Hashing function. A hash function takes a key as input and produces an integer value, known as the hash code. The goal of a good hash function is to distribute keys evenly across a limited range of integer values. A well-distributed hash function minimizes collisions. Collisions. A collision occurs when two different keys produce the same hash code. Collisions are unavoidable, as the range of possible keys is typically much larger than the number of available slots in the hash table. Collision resolution. Various techniques exist to handle collisions. Common strategies include separate chaining, or open hashing. Each slot in the hash table is a linked list. When a collision occurs, the new key-value pair is simply added to the linked list at that slot. Open addressing. When a collision occurs, the hash table probes for an empty slot nearby. Common probing techniques include linear probing, quadratic probing, and double hashing. Go's map implementation uses a combination of techniques, including separate chaining with dynamic resizing to maintain good performance. The specifics are implementation dependent within the Go runtime. 2. Go's map type. In Go, the map type represents a hash table. Its syntax is key type, the data type of the keys. The key type must be comparable, example integers, strings, booleans, pointers, arrays, structs where all fields are comparable. Slices, maps, and functions cannot be used as keys directly because they are not directly comparable. Pointers to those types can be used as keys. Value type, the data type of the values. This can be any valid Go data type. 3. Creating and initializing maps. There are several ways to create and initialize maps in Go. Using make. The most common and recommended way is to use the make function. Using a map literal. You can create and initialize a map with initial values using a map literal. Declare without initialization, 0 value. Declaring a map without make, or a literal creates a nil map. You cannot add elements to a nil map, you'll get a panic. 4. Adding, accessing, and deleting elements. Adding elements. Use the assignment operator, equals, to add new key-value pairs to the map. Accessing elements. Use the key within square brackets, to retrieve the corresponding value. Important. Accessing a key that doesn't exist in the map doesn't cause an error. Instead, it returns the 0 value of the value type. To check if a key actually exists, use the "OK" idiom. Deleting elements. Use the delete function to remove a key-value pair from the map. 5. Iterating over maps. You can iterate over the key-value pairs in a map using a for range loop. The order of iteration is not guaranteed to be consistent across different runs. Maps in Go are inherently unordered. 6. Map length, number of elements. Use the len function to get the number of key-value pairs in a map. 7. Maps are passed by reference. In Go, maps are passed by reference. This means that when you pass a map to a function, the function receives a pointer to the original map. Any modifications made to the map within the function will affect the original map. 8. Comparing maps. You cannot directly compare two maps using the equals operator. This is because the order of elements in a map is not guaranteed, and two maps could contain the same key-value pairs in different orders. Trying to compare with equals will result in a compile time error. To compare maps, you need to iterate over the keys in one map and check if the same key exists in the other map with the same value. Important notes on map comparison asterisk. Asterisk reflect.deep equal asterisk. While reflect.deep equal can be used to compare maps, it's generally less efficient than a manual comparison function, especially for large maps. It also has limitations regarding unexport fields in structs used as keys or values, and can panic if the keys or values are not comparable. Use it with caution. Asterisk custom comparison asterisk. If you need to compare maps with complex values, example slices, maps nested within maps, you might need to implement a custom comparison function that recursively compares the values. 9. When to use maps, and when not to. Maps are an excellent choice when asterisk fast lookups asterisk. You need to quickly retrieve values based on a key. Asterisk storing key value data asterisk. You have a collection of data where each item is associated with a unique identifier. Asterisk representing dictionaries or symbol tables asterisk. Maps are ideal for representing dictionaries, like a word and its definition, or symbol tables in compilers. However, maps might not be the best choice when asterisk order matters asterisk. Maps are inherently unordered. If you need to maintain the order of elements, use a slice of structs instead. Asterisk frequent iteration and order is important asterisk. If you frequently iterate over the entire data set and the order of elements is critical, a slice might be more efficient. Asterisk very small data sets asterisk. For very small data sets, example less than 10 items, the overhead of a hash table might outweigh its benefits. A simple array or slice might be faster. Asterisk need to minimize memory usage asterisk. Go maps can use relatively more memory than alternatives like slices, especially if not managed well. 10. Performance considerations and best practices. Asterisk pre-allocation asterisk. If you know the approximate number of elements you'll be storing in a map, pre-allocate space using make, map key type value type, capacity. This can prevent the map from needing to resize frequently, which can improve performance. Asterisk good hash functions. For custom types, if you're using a custom type as a key, ensure that the type's hash, method, or comparison logic, if using equality, provides a good distribution of hash codes. Poorly distributed hash codes can lead to excessive collisions and degrade performance. Asterisk avoid unnecessary copies asterisk. Since maps are passed by reference, avoid making unnecessary copies of large maps, as this can consume significant memory and time. Asterisk concurrency asterisk. Maps in Go are not safe for concurrent access from multiple coroutines without synchronization. If multiple coroutines will be reading or writing to the same map, you'll need to use a mutex or other synchronization mechanism to prevent race conditions. The sync.map type, available in the sync package, provides a concurrency-safe map implementation, though it has its own performance characteristics that might not be suitable for all workloads. Consider using channels to pass data between coroutines to avoid shared mutable state. Asterisk key selection asterisk. Consider the size and type of your keys. Larger keys will consume more memory. Choosing a key type that's easy to hash can improve performance. Strings are often a good choice, but large strings can impact performance. Integer keys are usually very efficient. Asterisk value type choice. Asterisk the choice of value type also affects memory usage. Larger value types will naturally increase the memory footprint of the map. Consider using pointers to structs if memory usage is a concern, but be mindful of the overhead of dereferencing pointers. 11. Concurrency with maps. Accessing a map concurrently from multiple coroutines without proper synchronization can lead to data races and unpredictable behavior. There are a few approaches to handle concurrent access to maps. Mutexes. The most common approach is to use async.mutex to protect the map from concurrent access. Using sync.rw mutex allows multiple readers to access the map concurrently, improving performance when reads are more frequent than writes. Sync.map. The sync.map type provides a concurrency-safe map implementation. It's optimized for scenarios where keys are often read but rarely written to. It uses techniques like read copy update, RCU, to minimize contention. Sync.map methods. Store, key, value interface, stores a key value pair. Load, key interface, value interface, OK bool, retrieves a value associated with a key. Delete, key interface, deletes a key value pair. Range, func, key, value interface, bool, iterates over the map. The function returns true to continue iterating, false to stop. Channels. Another approach is to use channels to serialize access to the map. Create a single coroutine that owns the map and communicates with other coroutines through channels. This approach avoids the need for explicit locking but can introduce more complexity. Choosing the right approach. Mutexes. Simple to implement, good for general purpose concurrency. Potential for contention if writes are frequent. Sync.map. Optimized for read-heavy workloads. Less efficient for write-heavy workloads or when keys are frequently written to and deleted. Channels. More complex to implement, but can provide fine-grained control over concurrency. Best suited for scenarios where you need strict serialization of operations. 12. Common use cases. Caching. Maps are commonly used for caching frequently accessed data. Counting occurrences. You can use a map to count the occurrences of different items in a collection. The key represents the item, and the value represents the number of times it appears. Storing configuration data. Maps are suitable for storing configuration settings where you need to quickly retrieve a value based on a configuration key. Implementing data structures. Maps can be used as the foundation for other data structures, such as sets, where the keys represent the elements of the set and the values are irrelevant. 13. Summary. Go's map type is a powerful and versatile data structure that provides efficient key value storage and retrieval. Understanding the underlying concepts of hash tables, how to create, manipulate, and iterate over maps, and the best practices for performance and concurrency are essential for writing efficient and robust Go code. Choose the correct synchronization mechanism if you need to access the map concurrently from multiple coroutines. Consider pre-allocation, appropriate key types, and value types to optimize for performance and memory usage. By mastering maps, you can significantly improve the performance and functionality of your Go applications.